Plate tectonics is a scientific theory that describes the movement and interactions of large, rigid plates that make up the Earth's lithosphere, the outermost layer of the Earth. These plates float on the semi-fluid asthenosphere beneath them and are driven by processes such as mantle convection, slab pull, and ridge push. Plate tectonics explains many geological phenomena, including earthquakes, volcanic eruptions, mountain formation, and the distribution of continents and ocean basins. Here's how plate boundaries and movement can be mapped. Identifying plate boundaries. Plate boundaries are areas where tectonic plates interact, resulting in various geological features and phenomena. There are three main types of plate boundaries: divergent boundaries, where plates move apart; convergent boundaries, where plates collide; and transform boundaries, where plates slide past each other. Plate boundaries are often associated with geological features such as mid-ocean ridges, subduction zones, and transform faults. Mapping plate boundaries. Plate boundaries can be mapped using various geological and geophysical data, including seismicity, earthquake locations and focal mechanisms, volcanic activity, topographic features, and magnetic anomalies. Seismic data from earthquake monitoring networks provide information on the location and depth of earthquakes, which often occur along plate boundaries. Volcanic activity, such as eruptions and lava flows, can indicate the presence of convergent or divergent plate boundaries. Topographic features such as mid-ocean ridges, trenches, and mountain ranges are often associated with plate boundaries and can be mapped using satellite imagery and digital elevation models, DEMS. Magnetic anomalies recorded on the ocean floor reveal patterns of seafloor spreading and help identify divergent plate boundaries. Monitoring plate movement. Plate movement can be monitored using GPS, Global Positioning System, stations located around the world. GPS measurements provide precise information on the horizontal and vertical motion of tectonic plates over time. In addition to GPS, other geodetic techniques such as satellite radar interferometry, INSAR, and ground-based radar can be used to measure crustal deformation associated with plate movement. Modeling plate dynamics. Plate tectonic models, such as the Euler-Pole method and the finite element method, can be used to simulate the motion and deformation of tectonic plates over geological timescales. These models incorporate data on plate boundaries, geological structures, and geophysical properties to understand the driving forces and dynamics of plate tectonics. By mapping plate boundaries and monitoring plate movement, scientists can better understand the processes driving plate tectonics and the geological hazards associated with tectonic activity, such as earthquakes, volcanic eruptions, and tsunamis.